Hello everyone. So in today's lecture, we're gonna talk about eigenvalue, eigenvectors. Eigenvector, eigenvalue, and how do we use this to construct the general multivariate normal distribution. Okay. Recall in our last lecture we talked about the quadratic discriminant analysis and the linear discriminant analysis, where the quadratic discriminant analysis requires the assumption requires a multivariate normal distribution, but there we assume they all have the same they share the same variance. Also for the linear discriminant analysis, we requires among the different class, the variance parameter are same. So those are quite a special case for the general normal distribution. So, and in our next lecture on the future classes, we requires and the multivariate linear regression, ridge regression, we requires multivariate normal distribution. So we wanted to some normal distribution in general. So in this case, you can think of normal distribution in x and in the y direction, they have the same variance. Okay, that's very restrictive assumptions. Okay, so in today's class, just give you some mathematics and statistics preparation for the future machine learning algorithms. Okay, so first let's review what is an eigenvector and what is eigenvalue. Okay, given a square matrix, for example, so maybe here I can just give you an example. Suppose the matrix is 1 over square root 2, 1 over square root 2, 1 over square root 2, negative 1 over square root 2. Square matrix means the columns and the row are same. So this is 2 by 2. So this is a symmetric matrix. So given you a square matrix A, okay, if we have a vector A times a new vector, so this is a vector, this is a D by D matrix, this A is D by D. This new is D by 1 vector. If this matrix multiplies a vector equals to a scalar times a vector. This is a scalar times a vector for some vector nu does not equal to 0. Okay. So So here just one example, a square matrix. If that's the case, then we say nu is eigenvector of A, okay, and lambda is the eigenvalue of A associated with the eigenvector nu. Okay, so that's just a mathematical definition of the eigenvalue and eigenvectors. So what that really means? Actually, there is a geometric interpretation. So actually, each vector is you can think a vector in the xy plane. So suppose this is a new vector. Okay. And in general, the matrix times a vector represents either rotate or stretch your vector. So A times nu usually represents you somehow manipulate this original vector nu somehow by rotation or by some stretch. But since this is the eigenvector, this has a very special case. This eigenvector means if you multiply A equal to nu, so this just equals to lambda times nu. Okay. For example, say if we say lambda equals to positive 2, so this means if we multiply A to this new vector, this just means we extend this, so this is just A times nu. Okay, so the direction is same, but the length is multiplied by 2. Okay, and then suppose we do it one more time. We apply the operation A again, so we get a even longer vector. So the double the length of the A nu. So this is A square nu. Okay, and we can plot one more. Okay, so this is even more. This is even longer. So this is just so A nu, this equals to, so 2 times nu, right? A square nu equals to 4 times nu. Okay, and A cube. So if you apply the A again, so this is A cube nu. So this is just 2 so the lambda this equals to, so okay, I'll write on here, A cube lambda nu is just equals to A square lambda nu, right? And this scalar you can take it out, so it's lambda A square nu. So this will equals to lambda times square A lambda A nu, and this will be lambda cube nu. So it's just lambda cube, so which is 8 times nu. So this is the A triple power nu. Okay, this is just equals to 8 times nu. So that's the property of the positive eigenvector. On the other hand, if we have the eigenvalue equals to, say, -12. What's that mean? What's that mean? So suppose now we have a vector. Suppose we have this is the original vector. Suppose this is the eigenvector. We can call this nu. So in this, suppose we have another eigenvector here, and we multiply the matrix A. Think about it. If you apply the A nu, this is just equals to lambda times nu. And in this example, it's just equals to -12 nu. So it changes the direction and take the length half. So if you take a transformation, so this will be opposite direction, and this is A times nu. Okay, you apply one more time. You flip again. You flip back and you take the length half. So you get opposite direction, and this is A square nu. Okay, and then you take you apply another A. What you can get is even smaller. You take another opposite sign, and then you take half length. So this is A cube nu. Okay, so that's the geometric interpretations of the eigenvalue and eigenvector. So that's very unique properties associated with matrix A. And there are also some other properties. Let me summarize you here. The theorem: if nu is the eigenvector of A, with eigenvalue lambda, then nu is also the eigenvector of A to the power k, any integer. You multiply A multiple times, you get another matrix, but the eigenvector is same. But the eigenvalue will be multiple to the power k. The proof is very simple. Actually, in this example, we already give you the sketch of the proof. So, for example, in order to show without loss of the generality, we can just prove A square if nu is the eigenvector of A square. Okay, so this will equals to A multiply A times nu. And we know for the eigenvector, V is eigenvector of A, so this equals to lambda times V. Okay, because this is scalar, you can take front, so this is lambda times A nu, and this is nothing but A lambda square times nu. Okay, so we complete the proof. You can follow the same procedure. You take a cube, false power, and so on. So there's another property. If A is a matrix is invertible, okay, then V is again the eigenvector of inverse of the matrix A. And the eigenvalue is nothing but 1 over lambda. Actually, the proof is also follows very similar way. So we can just apply the inverse matrix multiply nu, okay? Because we can just rewrite so because nu is a eigenvector with eigenvalue lambda, right? Okay, and actually we can just rewrite this as we can just write the doing a trick here is lambda. We can just write the lambda and 1 over lambda v. Okay, because this is just 1, right? And then we have A inverse. And now we know the A times nu, lambda times nu is lambda multiply A times nu. Okay, because this property. And we have the 1 over lambda nu, because A times A inverse give you the identity matrix. So this shows the eigenvalues of the inverse of the matrix is you take the inverse of the eigenvalues A. Okay, so in other words, when you take the inverse matrix, the eigenvector don't change, but the eigenvalues get inverted. When you square a matrix, the eigenvector don't change too. The eigenvalues get squared. Okay, so that's few properties. Let me pause a little bit and I will continue in next video.